Hello, and welcome to this quiet corner of the cosmos, where the mysteries of the universe unfold like a gentle bedtime story. I'm so glad you're here, perhaps curled up under a soft blanket, your head resting on a pillow, ready to drift into a peaceful journey. Let's take a slow, deep breath together, feeling the air fill your lungs, then release it, letting any tension slip away like stardust scattering in the night. Tonight, we're going to explore the vast, wondrous question of what the universe is expanding into, a puzzle that feels like a whispered secret from the stars. Imagine yourself floating in a vast velvet darkness, surrounded by twinkling lights, each one a galaxy, a story, a dream. The universe is like an endless ocean, with galaxies sailing like glowing ships, drifting further apart as the waves of space stretch beneath them. Science, you see, is like a lantern, lighting up little corners of this infinite night, inviting us to wonder, to dream, and to rest in the beauty of it all. Take another deep breath, and let your shoulders soften, sinking into the warmth of this moment. Picture yourself aboard a gentle cosmic breeze, weightless, carried along by the rhythm of the universe. The question we're pondering tonight is one that has captivated scientists and dreamers alike. If the universe is expanding, what lies beyond its edges? Is it an endless void, or something we can't yet imagine? This journey won't overwhelm you with equations or heavy facts, but instead, it will wrap you in a blanket of curiosity, letting you float through the wonders of space as you relax. The universe, vast as it is, feels almost like a friend tonight, sharing its secrets in a soft, soothing voice. Close your eyes if you'd like, and imagine you're gliding through this cosmic sea, the stars winking at you, each one a reminder that you're part of something grand, something timeless. Let's pause for a moment, breathing slowly, feeling the calm settle over you like a warm, gentle glow. The universe's expansion is like a slow, graceful dance, where every galaxy moves in harmony, yet drifts further apart with each step. Scientists have spent years peering through telescopes, piecing together this cosmic tale, and tonight, we'll follow their footsteps, but in a way that feels like a lullaby. You don't need to know all the answers to feel the magic of the question. Picture the universe as a great, unfolding book, each page revealing a new chapter of stars, galaxies, and mysteries. As you rest here, safe and warm, imagine yourself as part of this story, connected to every twinkling light you see in your mind's eye. The universe is vast, but in this moment, it feels close, like a friend whispering just for you. Before we drift further, let me ask you something gentle, something to connect us across this cosmic night. If you're listening, maybe tucked into bed or lounging in a quiet space, where are you right now? What time is it in your corner of the world? If you feel like sharing, leave a comment later to let me know. It's like sending a little starbeam across the universe to me. For now, let's keep floating, letting the worries of the day melt away like morning mist. The universe's expansion is a story that began long ago, with a scientist named Edwin Hubble, who looked up at the night sky and saw something extraordinary. His discovery changed everything, like finding the first note of a song that's still playing today. So, take one more deep breath, and let's drift toward that moment, where the universe first revealed it was growing, stretching, reaching out into the unknown. As we drift from the quiet embrace of the cosmos, let's settle into a gentle rhythm, like leaves floating down a serene river. Take a slow, deep breath and feel your body soften, ready to glide into a story that changed how we see the universe. Picture a night sky in the early 20th century, filled with countless stars, each one a tiny beacon in the vast darkness. Back then, most scientists believed the universe was still unchanging, like a grand painting fixed forever on a cosmic canvas. They thought the stars and galaxies were locked in place, eternal and unmoving, a comforting thought in its simplicity. But one man, Edwin Hubble, looked up with a curious heart and a powerful tool, ready to unravel a secret the universe had been whispering for eons. At the Mount Wilson Observatory in California, high above the world, Hubble peered through the Hooker telescope, a marvel of its time with its 2.5-meter mirror, catching the faint glow of distant objects. Imagine the telescope as a giant eye, gazing into the depths of space, collecting light that had traveled for millions of years to reach it. Hubble wasn't just looking at stars within our Milky Way. He was studying faint, misty patches of light that seemed to hover far beyond. At first, no one was sure what these smudges were, clouds of gas perhaps, or clusters within our galaxy. But Hubble, with his patient observations, began to piece together a truth that would shift the very foundation of our understanding. These weren't mere clouds, they were entire galaxies, vast cities of stars, each one a world of its own, floating in the immense sea of space. What Hubble saw next was even more astonishing. As he studied these distant galaxies, he noticed something peculiar about their light. When you look at a rainbow, you see colors spread from red to violet, each one a different wavelength of light. Hubble found that the light from these galaxies was stretched, shifted toward the red end of the spectrum. This wasn't just a quirk, it was a clue. Picture the sound of a train whistle as it moves away from you, its pitch dropping, growing deeper as it recedes. This is the Doppler effect, and it works with light too. When a galaxy's light shifts red, it means that galaxy is moving away from us. Its light stretched as it races into the distance. Hubble called this phenomenon redshift, a term that would become a cornerstone of cosmology. But Hubble didn't stop there. Night after night, he observed more galaxies, cataloging their light, measuring their distances. He used stars called Cepheids, which pulse like cosmic lighthouses, their brightness changing in a predictable rhythm. By comparing how bright these stars appeared to how bright they truly were, Hubble could calculate how far away their galaxies were. It was like measuring the distance to a far-off lantern by how faintly it glowed. What he found was breathtaking. The farther a galaxy was, the redder its light, meaning it was moving away faster. This wasn't just a few galaxies drifting apart, it was a pattern, a rule. The universe, Hubble realized, was not still, it was expanding, like a great breath that carried every galaxy away from every other. Imagine the galaxies as dancers on a vast stage, each one gliding away from the others, not because they're moving through the space, but because the stage itself is growing larger. This discovery, now known as Hubble's law, was like finding the first verse of a cosmic poem. The farther a galaxy is, the faster it recedes, as if the universe is stretching in every direction, pulling its wonders apart. Hubble's work showed that the universe had a history, a beginning. If galaxies are moving away now, then long ago they must have been closer together, packed tightly in a moment of unimaginable density. This idea planted the seed for what we now call the Big Bang, the spark that set the universe in motion. This revelation was a quiet revolution, a shift in thought as profound as realizing the Earth orbits the Sun. Before Hubble, the universe was seen as eternal, unchanging, a grand monument in the sky. But his observations showed it was alive, dynamic, a story unfolding across billions of years. Picture the galaxies as leaves on a vast cosmic river, each one carried by the current, drifting further apart as the river widens. The light from these galaxies, stretched and reddened, is like a message from the past, telling us of a universe that is growing, changing, alive. Hubble's telescope was his window, his way of listening to the universe's song, and what he heard was a melody of motion, of expansion. The beauty of this discovery lies in its simplicity. Hubble didn't need complex equations to see the universe's growth. He needed only light, patience, and a willingness to question. His work reminds us that science is a journey, a series of small steps that lead to grand vistas. Each galaxy he studied was a piece of the puzzle, a clue to the universe's vast dance, and yet this dance is gentle, slow, unfolding over billions of years, far beyond the rush of our daily lives. As you listen, picture those galaxies, their stars twinkling like fireflies, each one a world of possibilities drifting further apart in a quiet, graceful motion. Hubble's discovery also opened a door to a deeper question. If the universe is expanding, what does that mean for its past and future? If galaxies are moving apart, then long ago they must have been impossibly close, perhaps in a single point, a moment of creation. This idea, though, is just the beginning. The expansion Hubble saw wasn't just about galaxies moving, it was about the very fabric of space itself, stretching, growing, carrying everything with it. It's as if the universe is a vast tapestry, and every thread is being gently pulled, widening the pattern with each passing moment. This stretching, this expansion, is what we'll explore next, a story of space itself coming alive. As we float through this tale, let the vastness of Hubble's discovery settle over you like a soft blanket. The universe is not a still picture, but a living story, one that began with a single note and continues to unfold. The galaxies, with their red-shifted light, are like whispers from the cosmos, telling us of their journey. And yet, in this moment, you are here, safe, wrapped in the quiet of the night. Let the stars guide your thoughts, each one a reminder of the universe's gentle expansion. As we drift toward the next chapter, we'll explore how space itself is stretching, like a canvas that grows larger, carrying the galaxies along in its endless, serene dance. Let's glide gently from the dance of galaxies, where Edwin Hubble showed us the universe's grand motion, into a deeper layer of this cosmic story. Picture a vast, invisible canvas, stretching softly beneath the stars, its threads pulling apart in a slow, silent symphony. Take a moment to breathe deeply, letting your thoughts settle like dust in a quiet room. The universe's expansion, you see, is not about galaxies racing through space like ships across an ocean. Instead, it's the very fabric of space itself that's growing, widening, carrying every star and galaxy along with it. Imagine a loaf of bread baking in a warm oven, its dough rising, the raisins inside drifting farther apart as the bread expands. The raisins aren't moving on their own, the dough between them is stretching, just as space stretches between the galaxies, making the universe a living, breathing tapestry. This idea of space stretching is a strange and beautiful one. Unlike the way we think of movement in our everyday world, cars speeding down highways or birds soaring through the sky, the galaxies aren't traveling through some vast emptiness. Space itself is the stage, and it's growing larger with every passing moment. Picture a sheet of fabric, soft and shimmering, being gently pulled at its edges. The stars and galaxies are like beads sewn onto this fabric, carried apart as it stretches. This expansion happens everywhere, in every direction, a quiet unfolding that has been happening for billions of years. Scientists realized this when they saw that the redshift Hubble observed wasn't caused by galaxies speeding away, but by the space between them growing, like the surface of a balloon inflating, carrying dots farther apart. Now, let's linger on that balloon for a moment. Imagine blowing air into it, watching its surface grow, the distance between those dots increasing. The dots themselves aren't moving across the balloon, the rubber is stretching, pulling them apart. In the universe, galaxies are like those dots, held in place by the expanding space around them. This stretching is so subtle, so gentle, that it only becomes noticeable over vast distances, across millions or billions of light years. Close by, within our own galaxy or our solar system, the pull of gravity is far stronger than this cosmic stretching. The Earth doesn't drift away from the Sun, and the stars in the Milky Way stay bound together, like friends holding hands in a crowd. It's only when you look far out, to the distant galaxies, that you see the universe's expansion at work, like a tide pulling everything gently outward. This stretching of space changes how we see the universe. The farther away a galaxy is, the more space there is between us and it, and the faster it seems to move away. It's not that the galaxy is speeding through space, it's that more space is being created, like new pages added to a book, pushing the chapters farther apart. This is why the most distant galaxies have the strongest redshift, their light stretched into long red waves as space expands beneath it. Scientists measure this expansion by looking at how much the light shifts, like listening to the pitch of a song change as it fades into the distance. The more space there is to stretch, the faster the galaxy appears to recede, a pattern that holds true across the cosmos, a quiet rule written into the fabric of reality. But this expansion isn't just a story of galaxies drifting apart. It creates a kind of cosmic horizon, a limit to what we can see. Picture standing on a hill, watching ships sail away until they vanish beyond the curve of the sea. In the universe, some galaxies are so far away that their light struggles to reach us. The space between us is stretching so quickly that the light gets stretched too, its waves growing longer and fainter until they fade into invisibility. These galaxies aren't gone. They're still out there, shining, but the expanding space carries them beyond our view. This boundary, this edge of what we can see, is called the observable universe, a bubble of light and time that holds everything we can ever know. Beyond it, there may be countless more galaxies, but they're hidden, like stories in a book we'll never read. What's fascinating is that this stretching of space doesn't affect everything equally. On smaller scales, like within our own galaxy, gravity is like a gentle anchor, holding stars and planets together. Imagine a cluster of fireflies in a forest, their lights twinkling close together. The forest may grow larger, but the fireflies stay near, bound by an invisible force. In the same way, the Milky Way and its neighboring galaxies like Andromeda are held together by gravity, resisting the pull of expanding space. In fact, the Milky Way and Andromeda are on a slow collision course, drawn together by their mutual attraction, like two dancers moving closer while the stage around them widens. This balance between gravity and expansion is what shapes the universe, a delicate interplay of forces that keeps our local corner cozy while the distant cosmos drifts apart. Scientists have spent decades studying this expansion, using telescopes to peer at galaxies billions of light years away. They've found that the universe's growth is not just a steady push, but a process that's been unfolding since the beginning of time. When Hubble first saw the redshift, he didn't know the full story, but his discovery opened the door to understanding that space itself is dynamic, alive, changing. It's as if the universe is a painting that's still being drawn, its colors spreading outward with every brushstroke. This idea challenges how we think about the world. We're used to spaces that stay fixed rooms, cities, landscapes, but the universe is different. Its very essence is growth, a quiet, relentless stretching that carries the stars along. This stretching also raises a curious question. If space is expanding, what's it expanding into? Is there something outside the universe, a larger canvas beyond the one we know? Scientists say it's not quite like that. The universe doesn't need an outside to expand into because space itself is the thing that's growing. Picture a bubble of soap film, its surface shimmering and expanding. There's no need for an outside space. The bubble creates its own room as it grows. The universe might be like that, a self-contained expanse that makes its own space as it stretches. It's a strange thought, one that bends the mind, but it reminds us that the universe doesn't follow the rules of our everyday world. It's a place of wonder, where the very fabric of reality can shift and grow. As we ponder this, let's consider how scientists observe this expansion. They use tools like spectroscopy, which breaks light into its colors, revealing the redshift that tells us how fast galaxies are receding. It's like reading the fingerprints of the universe, each galaxy's light carrying a story of its journey. By studying thousands of galaxies, astronomers have mapped the expansion, creating a picture of a universe that's been growing for nearly 14 billion years. This work is slow, patient, like piecing together a mosaic from tiny fragments of light. Each observation adds a new piece, helping us see the grand design of the cosmos, a design that's always changing, always stretching. The beauty of this story is that it's not just about far-off galaxies or distant light. It's about the universe we're part of, the same space that holds our planet, our home. The expansion is happening all around us, but it's so gentle, so vast, that we don't feel it in our daily lives. The stars above us, the ground beneath us, are held together by forces stronger than the universe's stretch. Yet, out there, beyond our reach, the cosmos is unfolding, a quiet, endless process that began long before us and will continue long after. As we drift toward the next chapter, we'll explore the moment when this expansion began, a fleeting burst of growth called inflation, when the universe bloomed from a speck into a vast, star-filled wonder. As we drift from the gentle stretching of space, where galaxies float apart like leaves on a cosmic stream, let's journey back to the very beginning, to a moment when the universe itself was born. Take a slow, deep breath, letting your mind settle into the quiet vastness of this tale. Picture a time before stars, before galaxies, before even the light we see in the night sky. The universe, some 13.8 billion years ago, was not the sprawling cosmos we know today. It was a tiny speck, smaller than a grain of sand, smaller even than an atom, a point of infinite density and heat, holding all that would become the stars, planets, and us. Then, in a fraction of a second, something extraordinary happened, a burst of growth so rapid, so profound, it set the stage for everything we see. This was the cosmic inflation, a fleeting moment when the universe bloomed like a flower opening to the first light of dawn. Imagine this tiny speck, this seed of the cosmos, suddenly swelling, expanding faster than you can blink. In less than a trillionth of a second, it grew from smaller than an atom to something spanning light years, a vast canvas where the story of the universe would be painted. This wasn't just a slow stretching, like the expansion we see today. It was a violent, breathtaking surge, as if the universe took a deep breath and exhaled an entire cosmos. Scientists call this moment inflation, a theory proposed to explain why the universe looks the way it do, smooth, vast, and filled with the seeds of galaxies. Picture it as a spark igniting a firework, a single burst that scatters light and color across the sky, creating patterns that endure for eons. What made this inflation so special was its role in shaping the universe's structure. Before this moment, the universe was a chaotic soup of energy and particles, impossibly hot and dense. But as it expanded, it smoothed out, like a wrinkled cloth being stretched taut. This rapid growth flattened any irregularities, making the universe remarkably uniform, like a calm sea after a storm. Yet, within this smoothness, there were tiny ripples, subtle variations in density caused by quantum fluctuations, random flickers in the fabric of reality at the smallest scales. These fluctuations were like whispers in the early universe, so faint they were almost nothing, but as space expanded, they were stretched too, becoming the blueprints for galaxies, stars, and planets. These quantum fluctuations are a marvel of nature, a reminder that even the tiniest moments can shape the grandest outcomes. Picture a pond, still and quiet, where a single pebble drops, sending ripples across the surface. Those ripples, small at first, spread outward, shaping the water's flow. In the early universe, these quantum ripples were stretched by inflation, growing into vast patterns that would guide the formation of cosmic structures. Where the density was slightly higher, matter began to clump together, like grains of sand gathering in a stream. Over millions of years, these clumps grew into galaxies, each one a glowing tapestry of stars, held together by gravity's gentle embrace. Without inflation, the universe might have been a jumbled mess, too uneven to form the intricate web of galaxies we see today. Scientists came to this idea of inflation through careful study, piecing together clues from the universe's oldest light. They looked at the cosmic microwave background, a faint glow that fills the sky, a snapshot of the universe when it was just 380,000 years old. This light, captured by telescopes like the Planck satellite, shows a pattern of tiny temperature differences, like faint brushstrokes on a canvas. These differences match the predictions of inflation, showing that those early quantum ripples were stretched across the cosmos, setting the stage for everything that followed. It's as if the universe wrote its own origin story in this light, a story we're only now learning to read, like deciphering an ancient script under a soft, glowing lamp. The beauty of inflation is how it connects the smallest scales to the largest. Those quantum fluctuations, happening at sizes far smaller than an atom, were stretched to span billions of light years, shaping the universe's grand architecture. It's like a single note in a song, so soft it's barely heard, growing into a symphony that echoes across time. This rapid expansion also explains why the universe appears so flat and uniform when we look at it today. Without inflation, the cosmos might have been crumpled or uneven, with galaxies clustered in some areas and absent in others. Instead, inflation stretched space so thoroughly that it appears smooth, like a sheet of glass, with just enough variation to spark the formation of stars and galaxies. This moment of inflation was fleeting, lasting less than a blink, yet its effects are eternal. After it ended, the universe continued to expand, but at a slower, steadier pace, like a river settling into a gentle flow after a sudden flood. The energy that drove inflation transformed into the particles and forces that make up our world: quarks, electrons, light, and gravity. These building blocks began to weave together, forming the first atoms, then stars, then galaxies, all carried by the ongoing expansion of space. The universe, born in that explosive moment, became a vast stage, where the drama of creation continues to unfold, act by act, across billions of years. What's remarkable about inflation is how it answers questions we didn't even know to ask. For instance, why do distant parts of the universe look so similar, even though they're too far apart for light to have traveled between them? Inflation explains this by suggesting that these regions were once close together, squeezed into that tiny speck before the Great Expansion. As space ballooned outward, those regions were carried far apart, yet they retained the same character, like two pages torn from the same book. This idea, called the horizon problem, puzzled scientists until inflation offered a solution, a way to understand why the universe seems so cohesive, like a single melody played across a vast orchestra. The discovery of inflation came from theorists like Alan Guth, who in the 1980s proposed this idea to solve mysteries about the universe's structure. Picture Guth and his colleagues as cosmic detectives, sifting through clues in the light from distant stars, trying to understand the universe's first moments. They used mathematics and physics to model what might have happened, imagining a force called the inflaton field that drove this rapid expansion. This field, like an invisible wind, pushed space outward, then faded away, leaving behind a universe ready to form stars and galaxies. It's a story of imagination meeting evidence, a reminder that science is a dance between curiosity and discovery, each step revealing a new piece of the cosmic puzzle. As we linger on this idea, consider the scale of it all. The universe went from smaller than a speck to larger than anything we can imagine in a moment, so brief it defies comprehension. Yet, that moment shaped everything, every star, every planet, every breath we take. It's as if the universe was a seed, planted in an instant, growing into a vast tree of galaxies, its branches reaching across the cosmos. This story of inflation is not just about the past. It's about the foundation of the universe we live in, a foundation that continues to expand, carrying us along in its gentle, relentless motion. As we drift toward the next chapter, we'll explore a mysterious force that's pushing this expansion faster today, a force called dark energy, whispering through the cosmos like a breeze we can't quite catch. As we drift from the fleeting burst of cosmic inflation, where the universe bloomed from a speck into a vast expanse, let's glide into a quieter, yet equally mysterious chapter of the cosmos. Take a slow, deep breath, letting your thoughts soften like clouds dissolving in a twilight sky. The universe, born in that explosive moment, has been expanding ever since, its galaxies drifting apart like petals on a gentle breeze. But something unexpected happened billions of years later, a discovery that surprised even the sharpest minds. The expansion of the universe isn't just continuing, it's speeding up, pushed by an invisible force that scientists call dark energy. Picture it as a soft, unseen wind, whispering through the cosmos, nudging galaxies farther apart with a gentle but relentless push. This force, mysterious and elusive, is one of the greatest enigmas in science, a puzzle that invites us to wonder about the universe's hidden workings. Dark energy is like a shadow cast across the universe, invisible yet powerful, shaping its fate in ways we're only beginning to understand. Scientists estimate it makes up about 70% of the universe's total energy, far more than the stars, planets, or even the mysterious dark matter that binds galaxies together. Unlike matter, which clumps into galaxies and stars, dark energy seems to be spread evenly across space, like a faint hum that fills every corner of the cosmos. It doesn't gather or cluster. It simply exists, pushing against the pull of gravity, driving the universe to expand faster and faster. Imagine a vast ocean, its waves growing stronger, carrying ships farther apart with each swell. Dark energy is that unseen current, moving the galaxies in a quiet, unstoppable dance. This discovery came to light in the late 1990s, when astronomers were studying distant stars called supernovae. These are stars that end their lives in massive explosions, shining so brightly they can outglow entire galaxies for a brief moment. Picture them as cosmic firecrackers, bursting with light that travels across billions of years to reach our telescopes. Scientists use these supernovae as markers, like candles in the night, to measure distances in the universe. They expected to find that the universe's expansion was slowing down, pulled back by the gravity of all the matter within its stars, galaxies, and dust. But what they saw was astonishing. The light from these supernovae was fainter than expected, suggesting they were farther away than they should be. The universe, it turned out, wasn't slowing down. It was speeding up, as if some invisible hand was pushing the galaxies apart faster than ever before. This revelation was like finding a new verse in the universe's ancient song. Astronomers realized that something was counteracting gravity, a force that didn't pull things together, but pushed them apart. They named it dark energy, a term that captures its mystery as much as its effect. Unlike the light of stars or the pull of gravity, dark energy doesn't reveal itself directly. It's like a breeze you feel but cannot see, its presence known only through the motion of galaxies drifting ever farther. Scientists studied these supernovae with telescopes perched on mountaintops and orbiting in space, capturing their light to unravel the story of the universe's expansion. Each supernova was a clue, a snapshot of a moment billions of years ago, showing that the cosmos was growing faster than anyone had imagined. What makes dark energy so intriguing is its unknown nature. Is it a property of space itself, woven into the fabric of the cosmos, like a thread in a tapestry? Or is it something else entirely, a force we haven't yet grasped? One idea, proposed long ago by Albert Einstein, might hold a key. Einstein once introduced a concept called the cosmological constant, a kind of energy inherent in space that could balance the universe's gravity, keeping it static. When Hubble's discovery showed the universe was expanding, Einstein set this idea aside, calling it his greatest blunder. But decades later, when dark energy was discovered, scientists dusted off the cosmological constant, wondering if it might be the source of this mysterious force. Picture it as a quiet hum in the universe, a constant presence that grows stronger as space expands, pushing galaxies apart like ripples spreading across a pond. Another possibility is that dark energy isn't constant at all, but changes over time, like a melody that shifts its tune. Some scientists suggest it could be a dynamic field, something that evolves as the universe grows, perhaps growing stronger or weaker with each passing eon. This idea paints a picture of a universe that's not just expanding but transforming, its rules subtly shifting as it ages. Imagine a river that widens and quickens, its currents changing as it flows. If dark energy changes, it could alter the universe's future, speeding up the expansion even more or perhaps slowing it down in ways we can't predict. This uncertainty is part of what makes dark energy so captivating, a cosmic riddle that invites us to listen closely to the universe's whispers. The discovery of dark energy came from careful observations, not just of supernovae, but of the universe's large-scale structure. Scientists studied the way galaxies cluster together, forming vast webs of light and matter, like threads in a cosmic quilt. They found that these clusters are being pulled apart, stretched by the same force that dims the light of distant supernovae. By mapping these patterns, astronomers confirmed that dark energy is at work, shaping the universe's growth. Telescopes like the Hubble Space Telescope and ground-based observatories have been key, their lenses capturing light from billions of years ago, offering glimpses into the universe's past and hints of its future. Each observation is like a note in a grand symphony, adding to our understanding of this invisible force. Dark energy's influence raises profound questions about the universe's fate. If it continues to push galaxies apart, the cosmos could grow ever larger, ever emptier, like a gallery with its paintings slowly fading. In billions of years, galaxies might drift so far that their light no longer reaches us, leaving our night sky darker, quieter. This idea, though distant, feels like a gentle reminder of the universe's vastness, its changes unfolding over scales far beyond our own lives. Yet, dark energy also connects to the present, to the stars we see tonight, to the galaxies that shine across the cosmos. It's a force that's always been there, quietly shaping the universe, like an artist adding subtle strokes to a canvas that spans eternity. Scientists are still unraveling dark energy's secrets, using new tools and ideas to probe its nature. Missions like the Euclid Space Telescope, launched to map the universe's structure, aim to measure how dark energy affects the distribution of galaxies, like charting the flow of a cosmic river. These efforts are slow, patient, like piecing together a puzzle with no edges. Each new discovery brings us closer to understanding this force, but it also deepens the mystery, reminding us that the universe is full of surprises. Dark energy, in its quiet power, is a testament to the cosmos's ability to keep secrets, even from the brightest minds. As we linger on this enigmatic force, we see it as a thread in the universe's story, one that ties the past to the future. It's a force that doesn't just push galaxies apart, but shapes the very nature of space, making the universe a dynamic, ever-changing place. The stars we see tonight, the galaxies glowing in the distance, are all part of this great expansion, driven by a force we can't see but can feel in the motion of the cosmos. As we drift toward the next chapter, we'll explore a number that measures this expansion, a rhythm called the Hubble constant, which beats like a pulse in the heart of the universe, guiding us through its endless, gentle growth. From the gentle push of dark energy, nudging galaxies apart like a whisper through the cosmos, we now glide into a rhythm that measures the heartbeat of the universe's expansion. Picture a vast orchestra, each galaxy a musician playing its part, their notes drifting apart in a melody that spans billions of years. Take a slow, deep breath, letting your mind settle into the quiet cadence of this cosmic tale. This rhythm is captured in a single number, known as the Hubble constant, a key that unlocks the speed at which the universe grows. Named after Edwin Hubble, who first saw the galaxies receding, this constant is like a metronome, ticking out the pace of cosmic expansion, telling us how fast galaxies move away based on their distance from us. It's a number that weaves together the light of distant stars and the story of the universe's growth, a story written in the glow of the night sky. The Hubble constant is measured in kilometers per second per megaparsec, a unit that sounds complex, but is simply a way to describe vast distances. A megaparsec is about 3.26 million light-years, a stretch so immense it could hold countless galaxies. Imagine a cosmic ruler, marked not in inches but in light-years, measuring the space between us and the farthest stars. The Hubble constant tells us that for every megaparsec a galaxy is away from us, it moves away faster by a certain speed. If a galaxy is 1 megaparsec away, it might recede at, say, 70 kilometers per second. If it's 2 megaparsecs away, it moves twice as fast. This pattern, discovered through years of patient observation, is like a song with a steady beat, each galaxy playing its part in the universe's endless expansion. To find this constant, astronomers rely on special stars called Cepheid variables, which pulse like cosmic lighthouses. These stars brighten and dim in a regular pattern, their rhythm revealing their true brightness. Picture a lantern in a distant harbor, its glow flickering in a predictable dance. By comparing how bright a Cepheid appears from Earth to its actual brightness, scientists can calculate its distance, like judging how far a light is by its faintness. These stars are scattered across nearby galaxies, serving as markers in the vastness of space. By studying their light and measuring their redshift, the stretching of light as galaxies move away, astronomers can calculate the Hubble constant, piecing together the universe's expansion rate like a puzzle coming into focus. This process is delicate, requiring telescopes that can capture the faintest glimmers of starlight. Observatories like the Hubble Space Telescope have been crucial, their lenses gathering light that has traveled for millions of years. Picture astronomers as cosmic scribes, recording the stories told by these distant stars, each flicker a chapter in the universe's history. They use spectroscopy to break light into its colors, revealing the redshift that shows how fast a galaxy is receding. By combining these measurements with distances from Cepheid stars, they arrive at a number that describes the universe's growth. It's a slow, meticulous task, like weaving a tapestry thread by thread, each observation adding to the picture of a universe that's been expanding for nearly 14 billion years. But this cosmic measurement isn't without its mysteries. When astronomers calculate the Hubble constant, they find a curious puzzle, something they call the Hubble tension. Different methods of measuring the constant give slightly different results, like two musicians playing the same song but in slightly different keys. One method uses nearby galaxies, measuring their distances with Cepheids and supernovae, those brilliant explosions that act as cosmic beacons. This approach suggests a Hubble constant of about 73 kilometers per second per megaparsec. Another method looks at the universe's earliest light, the cosmic microwave background, a faint glow from when the universe was just 380,000 years old. This light, captured by telescopes like Planck, carries patterns that reveal the universe's expansion in its infancy. Using models of how the universe evolved, scientists estimate a lower Hubble constant, around 67 kilometers per second per megaparsec. This difference, though small, is significant. It's as if the universe is singing two melodies at once, and astronomers are trying to understand why. The discrepancy could mean there's something missing in our understanding of the cosmos, like a note we haven't yet heard. Perhaps dark energy, that mysterious force pushing galaxies apart, behaves differently than we think. Or maybe there's an unknown form of matter or energy, a hidden ingredient in the universe's recipe, affecting its expansion in ways we haven't accounted for. Picture the universe as a vast book, and the Hubble tension as a page where the words don't quite align, inviting scientists to read more closely, to search for clues in the light of distant stars. This tension has sparked a quiet excitement among astronomers, a reminder that the universe still holds secrets. They're using new tools like the James Webb Space Telescope to refine their measurements, peering deeper into the cosmos than ever before. Imagine these telescopes as windows into the past, capturing light that left its source when the universe was young. By studying more Cepheids and supernovae, scientists hope to pin down the Hubble constant with greater precision, like tuning an instrument to play the perfect note. They also look at gravitational waves, ripples in space-time caused by massive events like black hole collisions, which offer another way to measure distances in the universe. Each new observation is like a brushstroke, adding detail to the portrait of the cosmos. The Hubble constant is more than just a number. It's a key to understanding the universe's past and future. It tells us how old the universe is, about 13.8 billion years, by letting us trace its expansion backward, like rewinding a film to its opening scene. It also hints at the universe's fate, whether it will keep expanding forever or slow down under gravity's pull. Picture the universe as a river, its current measured by the Hubble constant, carrying galaxies along its flow. If dark energy continues to dominate, the river will quicken, spreading galaxies farther apart. If something changes, perhaps the river will slow, altering the course of the cosmic story. This constant also connects the vast scales of the universe to our own small corner. The same expansion measured by the Hubble constant is happening all around us, though we don't feel it in our daily lives. The stars in our galaxy, the planets in our solar system, are held together by gravity, like a family gathered close in a vast, stretching world. Yet, out there, beyond the Milky Way, the universe follows this rhythm, each galaxy moving to the beat of the Hubble constant. It's a reminder that we're part of something immense, a cosmos that's been growing since its first moments, guided by forces we're only beginning to understand. As we linger on this cosmic rhythm, we see the Hubble constant as a thread in the universe's tapestry, weaving together light, distance, and time. It's a number that captures the universe's pulse, its steady expansion carrying galaxies across an ever-widening stage. Astronomers continue to refine their measurements, chasing the truth like fireflies in the night, each new discovery a spark of understanding. As we drift toward the next chapter, we'll explore a boundary in the cosmos, the edge of what we can see, known as the cosmological horizon, where light and space meet in a quiet, endless dance. As we glide from the rhythmic pulse of the Hubble constant, measuring the universe's expansion like a steady heartbeat, we now drift toward a boundary that defines the limits of our cosmic view. Picture yourself standing at the edge of a vast, shimmering lake, its surface stretching to a horizon where the water meets the sky. Take a slow, deep breath, letting your thoughts settle into the stillness of this moment. In the universe, there's a similar edge, not of land or sea, but of light itself, a frontier called the cosmological horizon. This is the farthest reach of what we can see, a boundary where the universe's expansion carries galaxies beyond our gaze, like ships sailing past the curve of the Earth. It's a quiet, humbling limit, marking the edge of our observable universe, a bubble of light and time that holds all we can ever know. The cosmological horizon exists because light, though it travels at an astonishing 300,000 kilometers per second, has a finite speed. Imagine light as a messenger, racing across the cosmos, carrying the glow of distant stars and galaxies to our telescopes. But the universe is expanding, its space stretching like a vast elastic sheet, pulling those galaxies farther away as their light travels toward us. For the most distant galaxies, the space between us is growing so quickly that their light struggles to keep up, like a runner racing against a tide that's moving faster. Eventually, the expansion outpaces the light, stretching its waves so much that they fade into invisibility. This creates a boundary, a cosmic horizon beyond which we cannot see, no matter how powerful our telescopes become. This observable universe, the part we can see, is like a glowing sphere centered on Earth, not because we're special, but because light has only had so much time to reach us. The universe is about 13.8 billion years old, so you might think we can see 13.8 billion light years in every direction, but the expansion of space complicates this. As light travels toward us, the space it crosses stretches, making the actual distance to the farthest objects much greater. Scientists estimate the edge of the observable universe is about 46 billion light-years away, a number that feels almost dreamlike in its vastness. Picture a lantern's glow, spreading outward, but the ground beneath it stretching faster than the light can travel, carrying the farthest flickers beyond our reach. What lies beyond this horizon is one of the universe's deepest mysteries. The light from those regions hasn't had time to reach us since the universe began, and because of the accelerating expansion driven by dark energy, some of it never will. Imagine standing on a shore, watching waves roll in, knowing there are distant shores you'll never see, no matter how long you wait. Beyond the cosmological horizon, there could be countless more galaxies, stars, and planets, each with its own stories, its own light. But they're hidden from us, like pages in a book sealed shut, their tales lost to the stretching of space. This doesn't mean the universe ends at the horizon. It simply marks the limit of our vision, a veil drawn across the cosmos. The horizon is shaped by the universe's age and its expansion. When the universe was young, just a fraction of a second old, it was small enough for light to travel across it easily. But as space expanded, first rapidly during inflation, and then more steadily, the distances grew. Light from the farthest galaxies has been traveling for billions of years, a journey that began when the universe was a fraction of its current size. Picture that light as a letter, sent long ago from a distant friend, crossing an ever-widening ocean to reach you. By the time it arrives, the galaxy that sent it is far beyond where it was, carried away by the universe's relentless growth. This makes the observable universe a snapshot of the past, each star's light a memory from a different time. Astronomers study this light to map the observable universe, using telescopes that capture the faint glow of galaxies billions of light years away. The James Webb Space Telescope, for instance, peers into the infrared, where light from the most distant galaxies is stretched by expansion. Picture it as a cosmic ear, listening to whispers from the edge of time. These observations reveal galaxies as they were when the universe was young, their light just now reaching us after a journey across eons. By studying this light, scientists piece together the history of the universe's expansion, like archaeologists uncovering artifacts from a forgotten age. Each galaxy's redshift tells a story of how fast it's moving away, a clue to the shape and size of our cosmic bubble. The cosmological horizon also changes over time. As the universe expands, more light reaches us from farther away, slowly growing the size of the observable universe. But dark energy, with its accelerating push, complicates this. In the distant future, galaxies that we can see today may slip beyond the horizon, their light stretched so far it becomes undetectable. Imagine watching a ship sail away, its silhouette fading until it's gone, not because it sank, but because the sea itself grew too vast. In billions of years, the night sky might hold only the light of nearby galaxies, like the Milky Way and Andromeda, bound together by gravity. The rest of the universe could become a silent, unseen realm, hidden beyond the horizon's edge. This idea of a shrinking, observable universe is a quiet, poignant thought. It doesn't mean the universe itself is shrinking, only that our view of it is limited by the speed of light and the expansion of space. Scientists call this the cosmic light horizon, a boundary defined by the farthest light that has had time to reach us since the Big Bang. Beyond it, the universe continues, perhaps filled with galaxies, stars, and wonders we'll never know. Picture a library with endless shelves, but you can only read the books within arm's reach. The rest exist, but they're beyond your grasp, a reminder of the universe's vastness and our place within it. The horizon also ties to the universe's structure. The galaxies we see are part of a cosmic web, with filaments of galaxies stretching like threads between vast, empty voids. The expansion, driven by dark energy, stretches this web, pulling the filaments farther apart. But within our observable universe, we can still see these structures, like a map of glowing rivers against a dark sky. Telescopes like the Euclid Space Telescope are mapping this web, tracing the paths of galaxies to understand how the universe's expansion shapes its architecture. Each observation is like a brushstroke, painting a picture of a cosmos that's both vast and fleeting, its farthest reaches slipping away as we watch. This boundary, this cosmological horizon, invites us to ponder what we cannot see. Is the universe beyond it much like our own, with galaxies and stars scattered across an endless expanse? Or does it hold surprises, regions where the rules of physics twist in ways we can't imagine? The horizon keeps these questions just out of reach, like stars hidden behind a veil of night. Yet, it also reminds us of the beauty of what we can see, the galaxies that shine, the light that reaches us, the stories written in the cosmos. As we drift toward the next chapter, we'll explore whether the universe itself is infinite, a boundless sea, or finite, a closed book with no edges, waiting to reveal its next quiet secret. As we drift from the shimmering edge of the cosmological horizon, where light from distant galaxies fades like whispers lost in a vast night, we now turn to a question that feels both profound and serene, like gazing into an endless sea. Take a slow, deep breath, letting your mind settle into the quiet expanse of this cosmic mystery. The universe is expanding, its galaxies drifting apart, but is it boundless, stretching forever in every direction, or does it have a finite size, a shape with no edges? This question, whether the universe is infinite or finite, invites us to ponder the very nature of space, like wondering if an ocean has a shore or flows on without end. It's a thought that feels vast yet gentle, a puzzle that has captivated scientists and dreamers alike, as they try to map the contours of the cosmos. An infinite universe is a breathtaking idea. Picture a tapestry that never ends, its threads weaving galaxies, stars, and planets across an expanse with no boundary, no edge. In an infinite universe, you could travel forever in any direction and never reach a wall or a limit. Galaxies would stretch on endlessly, each one a glowing island in a sea without a horizon. The expansion we observe, where space stretches and carries galaxies apart, would simply mean that the distances between these islands grow larger, like ripples spreading across an infinite pond. This idea challenges our everyday sense of space, where everything has a beginning and an end, a room, a city, a world. But in an infinite universe, there's no final destination, only an eternal unfolding of stars and light. Now, consider the alternative, a finite universe, but one without boundaries. This is harder to picture, but imagine the surface of a balloon, round and limited in size, yet with no edges. If you walked along the balloon's surface, you'd never hit a wall, you'd just circle back to where you started. In a finite universe, space could curve in on itself like this, creating a cosmos that has a definite size but no borders. The expansion, in this case, would be like inflating that balloon, stretching its surface so the galaxies those dots on the balloon move farther apart. This kind of universe, called finite but unbounded, feels like a cosmic riddle, a space that's contained yet limitless, like a book with a fixed number of pages but no final edge. Scientists explore this question by studying the universe's structure, looking for clues in its oldest light and largest patterns. One key tool is the cosmic microwave background, a faint glow that fills the sky, left over from when the universe was just 380,000 years old. Picture this light as a photograph of the infant universe, its patterns like ripples frozen in time. By analyzing these patterns with telescopes like Planck, astronomers can estimate the universe's shape and size. So far, their measurements suggest the universe is remarkably flat, like a vast sheet stretched across the cosmos. A flat universe could be infinite, extending forever, or it could be finite, but so large that its edges are far beyond our reach, like a desert too vast to cross. This flatness is a clue, but it doesn't fully answer whether the universe is infinite or finite. A flat, infinite universe would expand forever, its galaxies spreading across an endless canvas. A flat, finite universe might curve in ways we can't yet detect, looping back on itself like a cosmic maze. There's also a third possibility. The universe could be curved, either closed like a sphere or open like a saddle. In a closed universe, the total mass and energy would be enough to bend space inward, potentially causing it to collapse in a future event called the Big Crunch. In an open universe, space would stretch outward forever, its galaxies drifting apart in an ever-thinning web. The flatness we observe leans toward an infinite or very large finite universe, but the question remains open, like a story waiting for its final chapter. The idea of an infinite universe sparks another fascinating thought: the multiverse. Some scientists propose that our universe is just one of many, a single bubble in a vast cosmic foam. Picture our universe as a glowing orb, floating alongside countless others, each with its own stars, galaxies, and perhaps even different laws of physics. This multiverse idea comes from theories of inflation, that rapid expansion in the universe's first moments. During inflation, space might have stretched in patches, creating separate bubbles, each one a universe of its own. Our universe, with its galaxies and expansion, could be just one of these bubbles, its boundaries hidden beyond the cosmological horizon, like islands lost in a misty sea. These other universes, if they exist, would be forever out of reach. The light from one universe couldn't cross into another, just as light from beyond our cosmological horizon can't reach us. Each universe might have its own version of expansion, its own stars, its own story. Some might be infinite, others finite, some filled with galaxies, others empty or strange. This multiverse idea is speculative, like a dream woven from mathematics and imagination, but it offers a way to think about what lies beyond our universe. If our universe is expanding, it might not be growing into another space, but simply stretching within its own bubble, one of many in a cosmic tapestry too vast to comprehend. Astronomers seek clues to this question by studying the universe's large-scale structure, the way galaxies cluster into filaments and walls, separated by vast voids. Picture the cosmos as a giant web, its threads glowing with galaxies, its empty spaces stretching wider as the universe expands. Telescopes like the Euclid Space Telescope map these patterns, tracing the paths of galaxies to see if space curves or extends forever. If the universe is finite and closed, the light from distant galaxies might bend, creating subtle patterns in the sky. If it's infinite, those patterns would stretch out evenly, like a canvas with no edges. These observations are like reading the universe's handwriting, each galaxy a letter in a script we're still learning to decipher. The question of infinity also touches on the nature of space itself. In our daily lives, we think of space as a fixed stage, a place where things happen. But in cosmology, space is dynamic, stretching and growing like a living thing. An infinite universe would mean that space has no limit, no boundary to mark its end. A finite universe might loop back on itself, like a path that circles around a mountain. Both possibilities challenge our intuition, inviting us to imagine a cosmos that defies the rules of our everyday world. Scientists use mathematics to model these ideas, equations that describe how space curves and expands, like notes in a song that's been playing for billions of years. As we ponder whether the universe is infinite or finite, we're reminded of its vastness, its ability to hold mysteries just out of reach. The galaxies we see, the light that reaches us, are part of a story that might stretch forever or curve back in a gentle arc. Either way, the universe's expansion continues, carrying its wonders farther apart, like stars drifting in a quiet night. This question, though unanswered, feels like a soft invitation to wonder, to let our minds explore the boundless possibilities of the cosmos. As we drift toward the next chapter, we'll explore the shape of the universe itself, whether it's flat, curved, or something else entirely, a cosmic form that guides its endless gentle dance. As we drift from the vast question of whether the universe stretches infinitely or curves within a finite embrace, we now glide into a new layer of the cosmic story, one that explores the very shape of the universe itself. Picture a grand, cosmic manuscript, its pages unfolding not as flat sheets but as surfaces that might bend, twist, or stretch in ways we can barely imagine. Take a slow, deep breath, letting your thoughts settle into the gentle rhythm of this tale. The universe's shape, whether it's flat like a boundless plane, closed like a sphere, or open like a saddle, guides its expansion, like the frame of a canvas directing the strokes of a painter. This shape, woven into the fabric of space and time, holds clues to how the universe began and where it might be heading, a quiet geometry that whispers of the cosmos's deepest secrets. The shape of the universe is not something we can see directly, like the curve of a hill or the edge of a table. Instead, it's a concept rooted in Einstein's theory of general relativity, which describes space and time as a flexible fabric, bent by the mass and energy within it. Imagine space as a vast sheet stretched across the cosmos, its form determined by everything it holds: stars, galaxies, dark matter, and dark energy. Scientists talk about three possible shapes: flat, closed, or open. A flat universe is like an infinite tabletop, where parallel lines never meet, and the angles of a triangle add up to exactly 180 degrees. A closed universe curves inward, like the surface of a sphere, where those lines eventually converge, and a triangle's angles sum to more than 180 degrees. An open universe, on the other hand, curves outward, like a saddle, where lines diverge, and a triangle's angles add up to less than 180 degrees. Each shape tells a different story about the universe's fate. In a flat universe, expansion could continue forever, slowing slightly as gravity tugs at the galaxies, like a breeze calming over time. In a closed universe, the mass and energy are so great that gravity might eventually halt the expansion, pulling everything back together in a cosmic collapse, known as the Big Crunch. Picture a balloon inflating, then deflating as its air is drawn back. In an open universe, expansion would also continue forever, but with less resistance from gravity, spreading galaxies thinner and thinner across a boundless expanse, like ripples fading across an endless lake. These possibilities, each tied to the universe's curvature, offer a glimpse into the cosmic narrative, a story shaped by the balance of forces we're only beginning to understand. To explore this shape, scientists turn to the universe's oldest light, the cosmic microwave background, a faint glow from when the universe was just 390,000 years old. This light, captured by telescopes like Planck, carries patterns like ripples on a pond, revealing the geometry of the early universe. By studying these patterns, astronomers measure the angles of cosmic triangles formed by the light's variations across vast distances. If those angles add up to 180 degrees, the universe is flat. If they're more or less, it's curved. So far, the measurements suggest the universe is remarkably flat, like a sheet stretched so tightly that any curve is too subtle to detect. This flatness is like a perfectly balanced melody, neither rising nor falling, but holding steady across the cosmos. This flatness is a puzzle in itself, a clue to the universe's origins. The theory of cosmic inflation, that rapid burst of expansion in the universe's first moments, offers an explanation. Picture inflation as a cosmic iron, smoothing out any wrinkles in the fabric of space, stretching it so vastly that it appears flat, like a crumpled cloth pulled taut. This process, happening in a fraction of a second, made the universe so large that any curvature is now too gentle to notice, like the curve of the Earth seeming flat when you stand upon it. The flatness we observe suggests inflation stretched space to an immense scale, creating a universe that looks uniform and balanced, a canvas ready for the galaxies to form. But flatness doesn't mean the universe's story is simple. Dark energy, that mysterious force pushing galaxies apart, plays a key role in shaping the universe's future, regardless of its geometry. In a flat universe, dark energy could drive an ever-accelerating expansion, spreading galaxies so far that the night sky grows dimmer over billions of years. Picture a tapestry, its threads pulling apart until the patterns fade into darkness. Even if the universe is flat, this acceleration could lead to a future where galaxies are isolated, like lone islands in a vast, empty sea. The interplay of dark energy and the universe's shape is like a dance, with each step determining how the cosmos will unfold. Astronomers measure this shape using not just the cosmic microwave background, but also the distribution of galaxies across the sky. Picture the universe as a cosmic web, with galaxies clustered into filaments, walls, and voids, like a network of glowing threads. Telescopes like the Euclid Space Telescope map these structures, looking for signs of curvature in how galaxies align. If space is curved, the light from distant galaxies might bend, creating patterns that hint at a closed or open universe. So far, these observations align with a flat universe, but they're like sketches in a notebook, still being refined as new data comes in. Each measurement is a step toward understanding the cosmos's form, like tracing the outline of a sculpture in the dark. The idea of a flat universe also raises questions about its size. A flat universe could be infinite, stretching forever, or it could be finite, but so vast that its edges are beyond our reach. Imagine a desert, its sands extending as far as you can see, with no horizon to mark its end. Whether infinite or finite, the universe's flatness suggests a balance between its mass, energy, and expansion. This balance, called the critical density, is like a scale perfectly poised, neither tipping toward collapse nor spreading too thin. The flatness we observe is so precise that it feels almost like a cosmic coincidence, prompting scientists to wonder why the universe is so finely tuned, like a stringed instrument playing a perfect note. This tuning connects back to inflation, which stretched the universe to such a scale that any initial curvature was smoothed out. But even in a flat universe, local curvature exists. Near massive objects like stars or black holes, space bends, creating gravitational wells that pull light and matter inward. Picture a heavy stone placed on a stretched sheet, dimpling its surface. These local curves don't affect the universe's overall shape, but they remind us that space is dynamic, shaped by the dance of mass and energy. On the largest scales, the universe's flatness guides its expansion, a steady unfolding that carries galaxies apart in a quiet, relentless rhythm. As we linger on this cosmic geometry, we see the universe's shape as a key to its story, a form that holds the history of its birth and the promise of its future. The flatness we observe, the balance it suggests, is like a canvas stretched tight, ready for the universe's next chapter. But dark energy, with its accelerating push, may reshape this story, driving the cosmos toward a fate we're still unraveling. As we drift toward the final chapter of our journey, we'll explore what this expansion might mean for the universe's end, whether it fades into a cold, dark silence, tears apart in a cosmic rip, or collapses back into itself, a story written in the stars and whispered in the night. As we drift from the boundless question of whether the universe stretches infinitely or curves within a finite form, we now glide into a new chapter, one that explores the very shape of the cosmos itself. Picture a vast, cosmic parchment, its surface not flat like a sheet of paper, but perhaps bending, folding, or stretching in ways that defy our everyday senses. Take a slow, deep breath, letting your thoughts settle into the quiet rhythm of this tale. The shape of the universe, whether it's flat like an endless plane, closed like a sphere, or open like a saddle, guides its expansion, like the frame of a canvas shaping the strokes of a cosmic painting. This shape, woven into the fabric of space and time, holds secrets about how the universe began and where it might be heading, a gentle geometry that whispers of the cosmos's past and future. This idea of the universe's shape comes from Einstein's theory of general relativity, which paints space and time as a flexible tapestry, molded by the mass and energy it holds. Imagine space as a vast cloth, stretched across the cosmos, its form determined by the weight of stars, galaxies, dark matter, and the mysterious push of dark energy. Scientists describe three possible shapes for this cosmic cloth: flat, closed, or open. A flat universe is like an infinite tabletop, where parallel lines stay parallel forever, and the angles of a triangle always add up to 180 degrees, just as they do in a school book. A closed universe curves inward, like the surface of a globe, where those lines eventually meet, and a triangle's angles sum to more than 180 degrees. An open universe, by contrast, curves outward, like a saddle, where lines drift apart, and a triangle's angles fall short of 180 degrees. Each shape tells a different story about the universe's journey. In a flat universe, the expansion could continue forever, slowing gently as gravity pulls at the galaxies, like a river calming as it flows. In a closed universe, the mass and energy are so dense that gravity might one day stop the expansion, pulling everything back together in a cosmic collapse known as the Big Crunch. Picture a balloon inflating, then slowly deflating as its air is drawn inward. In an open universe, the expansion would also continue forever, but with less resistance from gravity, spreading galaxies across a vast, thinning expanse, like ripples fading across an endless sea. These shapes, each tied to the universe's curvature, offer a glimpse into its destiny, a narrative shaped by the delicate balance of forces we're only beginning to grasp. To uncover this shape, scientists look to the universe's oldest light, the cosmic microwave background, a faint glow from when the cosmos was just 380,000 years old. Picture this light as a snapshot of the infant universe, its patterns like ripples frozen on a pond's surface. Telescopes like Planck capture these patterns, measuring the angles of cosmic triangles formed by variations in the light's temperature across vast distances. If those angles sum to exactly 180 degrees, the universe is flat. If they're more, it's closed. If less, it's open. The measurements so far point to a universe that's remarkably flat, like a sheet stretched so tightly that any curve is too subtle to detect. This flatness is like a perfectly tuned note, resonating across the cosmos with quiet precision. This flatness is a cosmic puzzle, a clue to the universe's origins. The theory of cosmic inflation, that explosive burst in the universe's first moments, offers an explanation. Imagine inflation as a cosmic press, stretching the fabric of space so vastly that any initial wrinkles were smoothed out, leaving a universe that appears flat, like a crumpled cloth pulled taut. This rapid expansion, happening in a fraction of a second, made the universe so large that any curvature is now too gentle to notice, like the curve of the Earth seeming flat when you stand upon it. The flatness we observe suggests inflation created a cosmos so immense that its shape feels boundless, a canvas ready for the stars and galaxies to form. Yet, this flatness doesn't make the universe's story simple. Dark energy, that unseen force pushing galaxies apart, plays a crucial role in shaping the cosmos's future, regardless of its geometry. In a flat universe, dark energy could drive an ever-accelerating expansion, spreading galaxies so far that the night sky grows dimmer over billions of years. Picture a tapestry, its threads pulling apart until the patterns fade into shadow. Even in a flat universe, this acceleration could lead to a future where galaxies are isolated, like lone beacons in a vast, darkening void. The interplay of dark energy and the universe's shape is like a cosmic dance, each step guiding the cosmos toward its next chapter. Astronomers explore this shape by studying the distribution of galaxies across the sky, mapping the cosmic web of filaments, walls, and voids. Picture the universe as a network of glowing threads, with galaxies clustered like beads along delicate strings, separated by vast, empty spaces. Telescopes like the Euclid Space Telescope trace these patterns, looking for signs of curvature in how galaxies align. If space is curved, the light from distant galaxies might bend, creating subtle distortions in the cosmic web. So far, these observations support a flat universe, but they're like sketches in a cosmic journal, still being refined as new data flows in. Each measurement is a step toward understanding the universe's form, like tracing the outline of a sculpture in the twilight. The flatness of the universe also raises questions about its balance. A flat universe sits at a critical density where the total mass and energy are perfectly poised, neither collapsing under gravity nor spreading too thin. Picture a scale, its arms perfectly level, holding the weight of the cosmos in equilibrium. This balance is so precise that it feels almost like a cosmic coincidence, prompting scientists to wonder why the universe is so finely tuned, like a stringed instrument playing a flawless chord. This tuning ties back to inflation, which stretched the universe to such a scale that any initial curvature was smoothed out, leaving a cosmos that appears flat and uniform. Even in a flat universe, local curvature exists, Near massive objects like stars or black holes, space bends, creating gravitational wells that curve light and pull matter inward. Imagine a heavy stone placed on a stretched sheet, dimpling its surface. These local curves don't affect the universe's overall shape, but they remind us that space is dynamic, shaped by the interplay of mass and energy. On the largest scales, the universe's flatness guides its expansion, a steady unfolding that carries galaxies apart in a quiet, relentless rhythm. This interplay of local and cosmic scales is like a symphony, with each note contributing to the universe's grand melody. As we linger on this cosmic geometry, we see the universe's shape as a key to its story, a form that holds the history of its birth and the promise of its future. The flatness we observe, the balance it suggests, is like a canvas stretched tight, ready for the universe's next act. But dark energy, with its accelerating push, may reshape this story, driving the cosmos toward a fate we're still unraveling. As we drift toward the final chapter of our journey, we'll explore what this expansion might mean for the universe's end, whether it fades into a cold, dark silence, tears apart in a cosmic rip, or collapses back into itself, a story written in the stars and whispered in the quiet of the night.